In this video, let's talk about the assumptions of linear regression. Now, the first thing that comes to my mind is normal or Gaussian distribution. So, we need to have our data normal and Gaussian distribution to get trained well, right? Suppose we have an axis here like this and our data is distributed like this. Now, looking at this graph, it clearly says that this is a Gaussian distribution because we have our data symmetrical, right? We have our data symmetrical from the middle. Now, suppose we don't have our data normally distributed. Suppose let us say that we have data something like this, right? Now, in this case, we need to apply some methods where we can bring such kind of data to the normal distribution. Then only our model will get trained well. Now, the second assumption is standardization. Standardization. Now, what is standardization here? Let us take an example of gradient descent problem. Suppose suppose we have a graph like this. We have a graph like this. Standardization is very important for the gradient descent problems. Okay. Now suppose if we have a data point somewhere here, if we have a point here. Now it will take a lot of time to reach this point which is called as a global minimum, right? Now standardization is really important because when we are training the data, we need to process the training quickly. Suppose if I have data somewhere here, then it will process the training very quickly and it will reach to the global minimum very fast. Now by applying standardization in the sense we are trying to scale the data, right? Scaling data. When we actually scale data, it will be in the range of plus minus 3 to plus 3. So this is how we will scale. Like how do we scale this data? Basically we apply z-score. In z-score we have mean is equal to 0 and standard deviation is equal to 1, and our formula will be x is a data set x minus mu by sigma. So when we apply this formula, we'll get the values in the range of minus 3 to plus 3. So this is about the standardization. And the next thing is a linearity. Suppose if we plot a graph with respect to the data set, suppose we have x and y and we have data something like this between x and y axis. So by looking at this graph, we can say this is purely a linear graph, right? Not purely, but approximately it is a linear kind of thing. Now, if we apply model for this, then it will be definitely going to train well. Suppose if we have a data something like this, which is not really a linear, suppose it is like this, then there is no collinearity. In such case, we should not apply a linear regression. Definitely, if we apply, definitely it will definitely give a bad model, right? So this is about a linearity. Now coming to the fourth one, multicollinearity. Multicollinearity. Let's see what is multicollinearity. Let's see what is multicollinearity. Suppose we have a data set having features x1, x2 and x3 are the input features, okay, and we have an output feature of y, okay. Now suppose we have this data. X1 and X2 are strongly correlated with output, approximately let us say 90% correlated with output, this X2 and X3 feature. Now it is not necessary to use both the features in the model. We can take either X2 or X3. Either of the one we can eliminate from the model, right? So that is about a multicollinearity. So this is it in this video. These are the assumptions of linear regression. In our next video, I'll talk about more. Thank you for watching.